Hi all. So today we're going to talk about this problem, 8.3, about a sliding ladder, and it's asking us like when it loses contact with the wall, what is the horizontal component of the velocity of the center of mass? So let's draw a free body diagram first. So length L, let's call this center of mass, which is in the middle of this ladder, so this is L/2. Let's just call it R, so then it's easier to write later. And then we know, let's draw a free body diagram. So this would be gravity. And here's a normal force, and here's a normal force. Let's call this N1 and N2. And so let's think about what happens when it loses contact. Well, when it loses contact, we know that N1 becomes 0. So now we would try to find the horizontal component of the velocity of the center of mass when N1 equals to 0. But it is actually quite hard, so let's think about it another way. So what happens to the horizontal component of the velocity of the center of mass when it's in contact with the wall, or when the ladder is in contact? Well, we know that the net force, F net, so in the x direction, is just N1. And as long as N1 doesn't equal to 0, the acceleration in x doesn't equal to 0. And so we know that V, the center of mass, the center of mass velocity, the x component, will keep increasing. And as soon as it loses contact, N1 becomes 0, and so does acceleration in x direction. And so V, center of mass, x, just equals it just stays constant. And so also we know that this is a maximum value, right? So now our problem now is, what is the maximum horizontal component of the velocity of the center of mass? And so let's try to find that. So this problem is actually quite complex if we just try to analyze the forces, because you will need to add a lot more constraints like x, let's call this x, and y. So we know that, so we need to also write x squared plus y squared equals to L squared, and then we have to differentiate to get the accelerations constraints, and then analyze the force, which is really complex to do. So what do we do when forces are too complicated? Well, we think about energy, right? So let's try to write energy. So in this case, the energy is always conserved. So let's draw the diagram again. So like, let's say this is L. So like when the rod is just vertical and the center of mass is here, and this is L/2. Let's call it R. What is the potential energy? So we know in this case it's mgr. And what happens when it falls a little distance? So again, L, center of mass is this one, and then R. Let's call this angle theta. And so if this angle is theta, this is 90 degrees. And so this is 90 degrees, then this angle would be 90 minus theta. And so this is theta. And so we know that this height here is R cosine theta. And so in this case, it is the potential energy is mgr cosine theta. And so this is the change in potential energy. And it's equals to the change in kinetic energy. And there are two terms. So you have the translational plus the rotational. So equals to half v center of mass squared plus half moment of inertia omega squared. Let's write omega as theta dot. So because omega equals to d theta dt, and let's write like theta dot, so it's easy. So now we can't really solve anything here yet because we have two unknowns. We have v, c, m, and theta dot. So it might be tempting to just say straight away, oh, like v, c, center of mass is equals to r theta dot. But remember, this relation, we need to prove it. We haven't proved this yet. So to do that, we will use a little bit of geometry. So again, I'm going to draw the diagram. We got the rod here, center of mass, R, R. And so let's try to recall some properties about the right triangle. So we know that median of the hypotenuse is equal to the distance to the midpoint. So like, in other words, like this distance. So this distance here. So like from this point to the midpoint equals to half of L, which is R. So now we know that this center of mass point is in a circular motion. So just to make this a bit more obvious. And by the way, you can search up this property online, but just in the interest of time, I'm not going to prove it here. So we have L, center of mass, R, R, and using that property, I'm gonna draw a dash line just so we know it's not actually a rod or something. So this is R, and we set this as theta previously. And so because this is theta, 90 degrees, this is 90 minus theta, and so this is also theta. And so it's quite easy to see that as theta changes, this center of mass goes in a sort of circular motion of radius r. And so now we've shown that VCM equals to r theta dot. And now let's rewrite the energy term. So I'm gonna rewrite the original one first. So mgr minus mgr cosine theta equals to half m VCM squared plus half I omega to theta dot squared. And we know VCM equals to r theta dot. And so mgr minus mgr cosine theta equals to half mr squared theta dot squared plus half, and then moment of inertia, let's just write it as beta mr squared. So beta mr squared theta dot squared. And let's factorize, and so what do we get when we factorize? We get half r squared theta dot squared m plus actually sure, let's do, we can also factor out an m, and then 1 plus beta equals to, and then here we can factor out m, and then g, mg, and also r, mgr 1 minus cosine theta. And so m cancels, and we're left with this expression. So g r 1 minus cosine theta equals to half r squared theta dot squared 1 plus beta. And remember what we're trying to find here. We're trying to find an expression for, so we're trying to find the horizontal component. So let's write as VCMX, the expression for this. So we need a VCM in this expression. So remember that we said VCM equals to r theta dot. So we have it here. So let's rewrite it. So gr1 minus cosine theta equals to half VCM squared 1 plus beta. And let's try to isolate VCM here. So VCM squared equals to gr1 minus 2gr1 minus cosine theta 1 plus beta. And so VCM equals to square root 2gr1 minus cosine theta 1 plus beta. And so what is the horizontal component of it? So just to make this clear, I'm going to draw a diagram again. So we have a rod here, length L, center of mass here, and then it's R, theta. And I'm just going to draw the line again, just so it's R is a circular motion. And so we're trying to get x, the x coordinate. So how do I, so V, the velocity of center of mass, the horizontal component, is basically the x dt. So like, let's call this point xy. So like the coordinate of the center of mass is xy. And so the horizontal component of the velocity would just be the change of x with respect to t. And so let's try to do this, to find this expression, let's try to find the expression of x and y first. So remember, this is theta, right angle, 90 minus theta, and so this is theta too. So we know x of the center of mass equals to r sine theta, and y cm equals to r cosine theta. So that's like the unit circle, right? Sort of. And so dx cm dt equals to, we know r is a constant, so we don't need to care about it. So r cosine theta. And remember the chain rule, so theta dot. And so basically this expression is equal to, so vcmx is equal to this. And let's rearrange it. And remember this expression is vcm just, so vcmx equals to vcm cosine theta. And so we get the expression, so vcm cosine theta equals to 2gr 1 minus cosine theta over 1 plus beta cosine theta. And so now how do we find the maximum of this expression? Well, we just find the point when the derivative of this is 0. So what's the derivative of this? So we're just trying to find the point where dv cmx over d theta equals to 0. And so let me just grab my calculator. So we find that when theta is about 48.2 degrees, the derivative is 0. And so when theta is about this degrees, so vcmx is just max. And so as aforementioned, this is the point where ladder loses contact. And also just a little bit of technique when you're using the calculator, like we know that this part is constant, so like we can rewrite this as sort of like, so we can rewrite vcmx as just 2gr 1 plus beta square root 1 minus cosine theta. And when we're trying to find the derivative, we don't need to care about this part because this is just a constant. And so we just plug this into the calculator and it'll be much faster. And so when theta equals to 48.2 degrees, that's the point where the ladder loses contact. And then we find that this is independent of beta. So remember our previous definition of I equals to beta mr squared. And so it is independent of this. But just to come back to this problem, we know it's a rod, it's a ladder. And so the moment of inertia should be 1/3 mr squared. And so just plugging these values back into the expression here, we find that vcmx equals to square root 2gr over 3. And so this is basically, because we define r as over 2, this is just equals to square root gl over 3. And so this is the final horizontal component, and also is the maximum velocity, maximum horizontal velocity. And so now this is basically the answer right here. And I hope you enjoyed this video, and thank you for watching.